The next presentation is about verifiable computation for approximate homomorphic encryption schemes, and Antonio Guimarães will give the talk.
Okay, thank you. So to start with a bit of context, let's say you're doing your FHE computation. This is just an example of context, but this is not the only use case. So you have your input data, you have your code, you're encrypting everything, you send to the cloud does all the encrypted processing and send it back to you. This is very nice, but FHE doesn't cover everything. If we take a closer look at this code, it can be anything, right? It's FHE. Let's say it's this neural network. And you're sending this to the cloud, and if the cloud is an honest or semi-honest environment, it will be computing the circuit that you wanted. But if the cloud is not, if it's a malicious environment, it might be computing something else. So you want some way of verifying this, and for that, you have verifiable computation. Again, the workflow is the same. You send your input data, you send your code. Now the cloud is not just processing, it's also proving that the processing that it's doing is correct, that it's actually running what it was asked to run. And it returns a proof to you that you can efficiently verify. Clearly, these two things, they go hand to hand. Like, you want to have both in a real-world scenario. And we can have both, like both are functionally complete. There are several ways of combining both. But the difficulty is to combine both efficiently. To give a bit of an overview of what we have so far, essentially we have two different main approaches. The first one is represented by these two lines of research. These are just two examples of many works that do that. And the point is that proof systems, the things that we need, that we use to prove this computation, they are very good for field arithmetic. So you can prove native arithmetic, the arithmetic part of FHE really well, but they struggle a bit with the part that is not algebraic. So we have key switching operations, bootstrapping operations, and that becomes very expensive for them. A new line of work that came out a few years ago, this inverts a bit the approach. Instead of trying to prove FHE, what this line of work, HIOPs, do is to homomorphically evaluate part of the proof system, and that enables them to have very efficient not only arithmetic, but also key switchings and bootstrapping, but that comes with certain disadvantage. Two of them that I will mention here, the first is public verification. You can have some notions of public verifiability in HIOPs. I think the next talk will give some details about it, but you cannot have a full-fledged, stronger definitions of public verifiability. And the second, which is our main point here, is approximate schemes. This type of approach, they rely on the FHE scheme essentially emulating or efficiently having field arithmetic, which cannot be achieved, at least not natively, by CKKS. You need some additional effort if you want to do that. What we are doing here is to follow this original traditional approach, and what we are introducing is a lot of building blocks and a lot of things to really have efficient key switching and rescaling, efficient non-algebraic operations. For bootstrapping, it's something that we don't cover it specifically, but we also don't see any issue with that, so we also should be able to have it. But we leave it more as a future work, since bootstrapping requires some special parameters as well. Okay, this is a brief overview of our solution. There are several building blocks and optimizations and improvements to all of them. I will try to give more an FHE view of all of this, focusing specifically on our proof-friendly CKKS, because I think that's more close to this community. Okay, to start, before the proof-friendly CKKS, we need a proof-friendly ring. And the motivation here is that the usual ring that we use for FHE is not really great for the proofs. This is the usual ring for FHE. We are probably very used to see this. These are usual parameters for schemes such as BGV, BFV, and CKKS. And the problem with this is big. Like, it's difficult to do computation on that, so what we rely on is RNS, or double CRT. Essentially, we get that huge ring, and we split it in components. This is the RNS splitting. And then we do another CRT, which is the number theoretical transform. Some schemes do FFTs, but for us, we're focused on an entity that splits the ring again, the subrings again, into small components. And these small components, you can have efficient arithmetic, because these components are very small, like they are smaller than a word size of a typical computer, let's say 50 bits prime. The problem with that is that in the proof system, you have a concept of soundness. So if you think about security, soundness would be the chance or how hard it is for someone to fake the proof, let's say. So you want to have both security and soundness, of course. And soundness in a proof system is, at least the ones that we are using, it's proportional to the smallest subcomponent of the ring. So for this ring, this good ring for FHE, we have 50 bits of soundness. And of course, we don't want that. We want 128 bits in the same way that we want for security. Solution so far, if you have 50 bits of soundness, you run 4 times, you repeat your computation 4 times, and you get 200 bits, and it works. The problem with that, of course, if you're running 4 times, you have a 4 times slowdown. And I didn't even start talking about the problems that we have here, so we would have 4 times slowdown right at the beginning, which is quite bad. Our solution for this, to save this 4 times, is to change slightly this ring so that it is good for the proofs and that we can still do efficient arithmetic. So if we look again at the splitting, this is the splitting that defines the number theoretical transform. And usually in FHE, you will always see this with d equals to 1, so that these maps to small components. But it doesn't need to be like that. Like this is for fully splitting or entity-friendly rings. You could have d equals to 2, which is almost fully splitting or almost entity-friendly. And with that, your soundness increases. Now your smallest component is bigger. So we can have soundness just by doing this small change in the ring. And the obvious question is, how can we still have efficiency with that? And the answer is actually, we found the answer actually in the the post-quantum crypto literature, that some people were using already incomplete entities which work over these rings. And in post-quantum crypto, they are actually used to give performance in some crypto systems. Here we don't actually manage to get performance out of this, even because this is just a proof of concept implementation. But you get a very, very small slowdown. It's just 5% for d equals to 2. So in the past, you would repeat 2 times. Instead of repeating 2 times, you only pay 5%. Instead of repeating 4 times, you would pay 20%. So I would say that this is a near optimal solution for combining these 2 things and have a proof-friendly ring. Okay, this is the ring, and we want to do everything over this ring and only this ring. Now, to the proof. I will go through CKKS showing how we prove it, but before, let me introduce our proof components. So we have 3 of them. The 2 of them are most important for now. So we have custom GKR. For those who know, GKR is essentially a proof system that is very good for arithmetic stuff. We kind of have a customized version of it. I will explain why customized later. But the point is, everything that is arithmetic goes in this box. Everything that is not arithmetic, as I will show, will be a range proof. So we want to prove that a vector or a polynomial in RQ has its coefficients smaller than some bound. That goes into this second box. It will become more clear as I go through CKKS. Okay, so briefly overview of CKKS. It's an approximate scheme. You have message and noise kind of mixed there. If you look inside the ciphertext, your ciphertext is a pair AB in RQ squared. I think that's probably most people are used to it. And in the next slides, I will represent the RNS components. So this pair AB is represented by these 2 vectors, where each square itself is the RNS component of CKKS. That matters because we are really wanting to do a full RNS CKKS so that efficiency is kept. CKKS adding is just really adding the components. It's pure algebraic, so we just put this in the custom GKR box. We don't have any issue with that. Previous literature also didn't have many issues with that, so no much novelty here. CKKS multiplication. Now, it's a bit more interesting. The first step is usually called pre-multiply or tensor product. And here it's also full algebraic. This is the equation that you need to run to do this pre-multiply step of CKKS. And if it's purely arithmetic, we can also easily prove. And previous literature also could. The next step is the key switching. So as you can notice, once you do the tensor multiplication, you get a ciphertext with 3 components. And you don't want that. You want a compact scheme. You want to reduce this to 2 components again. So you need a key switching or linearization. And that's a non-algebraic procedure. One question is, could we stop here? And that's actually what previous literature do. Like a lot of previous work, they stop here, they don't do the key switching, and they let things grow. And that works, of course, but it's not compact anymore unless you bound depth or change a bit the definitions. So no, we don't want to stop here. We want to have an efficient key switching. And what we do is that instead of proving the nonlinear part, the non-arithmetic part of the key switching, we do something different. So if we look at the equations of the key switching, you will have at some point a decomposition. It depends, there are several types of decompositions, but at some point you will do something similar to a decomposition or maybe go to a higher modulus, something that is not algebraic. What we do instead is, instead of doing this CRT minus 1, which is the decomposition, we ask the prover to do some decomposition. We are asking the prover to do this decomposition, but we let the prover do any decomposition. So the prover gives us a decomposed vector, W, and now we are going to check 2 things. One, that the decomposition, that recomposing it was correct. So if we recompose, this is a recomposition check. We are doing the CRT, and we are checking if this is correct. Notice that recomposing is pure algebraic, so we don't have a problem with it. And the second thing that we are doing is checking that every component is bounded by some value. So with these 2 things, we get the correctness because of A, and we get the small noise because of B. So we get what we want for the crypto system, even if the prover did not provide the right decomposition. We just want it to be correct, even if it's different from what we asked the prover to do. Then, of course, we continue the computation, and as you can see, arithmetic part goes to custom GKR, range proof goes for our range proof or RQ, and we can continue. To be clear, this depends on these building blocks being efficient, and at the end I will show that we get some contributions to them to really make them efficient. Okay, we continue. We have now a rescaling. A rescaling is basically a mod switching. We are dividing, doing a real division over the ciphertext. And this is also a non-algebraic operation, and we do something similar to what we've done for the key switching. I will not go into details, but it's pretty much the same. We turn it into range proofs and arithmetic so that we can put it in these boxes. A last problem that we have is that if you notice here, when we do the key switching, we are dropping one RNS component. And that's true for any mod switching that you do in FHE. You're changing the modulus. And that is a problem because, like I said, we want a single ring. And now we have 2 rings. We have RQ. OK, my pointer doesn't go there, but you can see. And we have RQ2 at the end. And we don't want this change. So here we would go further, and that would change the ring again. So what we do here is essentially an abstraction. Like in terms of implementation, doesn't change much. But essentially, we redefine the rescaling to embed the result back into the original ring. So you can see that as instead of changing the modulus, we're moving the ciphertext, the part that we care about the ciphertext, to an ideal of the original ring. So if you look at the RNS components, instead of dropping these components, we are just zeroing it. And now we keep the same ring, and the proofs can all be done over the same ring. Performance-wise, nothing changes, because the honest prover, it knows this is 0, and the honest prover doesn't need to compute zeros. Like, well, it can compute, but it's 0. As you continue, you are basically zeroing new components of the RNS representation here. And of course, we change key switching keys and everything else to also be in this specific ideal and keep things in this specific ideal. And with that, we have all the CKKS defined over a single ring, with the performance still improving because we are obviously ignoring these zeros. Okay, in summary, this is our proof of plain CKKS. We changed the ring, we changed the way that we prove the key switchings. We also allow for other decompositions if the prover is able to come up with something. And we do a noise analysis for this, and we show that it's basically the same behavior as the original CKKS with very minor differences. In terms of performance, we only have a slowdown because of the almost entity-friendly ring. So we can see that the performance is very close to the original CKKS that we implemented using Hexel. Okay, to the proof, to the components, we need these components to be efficient so that everything that I showed before is also efficient. The custom GKR one, this is a representation of everything that I showed so far. So every time I was putting something inside the box, it's this. If we open all the boxes, we have the green part is the custom GKR, and the yellow part would be our range proofs. As you can see, for one multiplication, you generate a circuit like this. If you have two multiplications, you would generate another circuit like this. And this is a very fixed circuit. And for those who know GKR, you know that you would implement this in normal GKR as a sequence of multiplications and additions, which works, it's efficient, but we can do better because this is a very fixed and structured circuit. So we call this circuit AC. And since it's a fixed circuit, we can do a very specific structured version of GKR where we have gates that are meant specifically for these operations. So our custom GKR is basically has constant depth 4 GKR. Abstracting it a bit, it means that the verifier will be efficient. It's also not affected by the recent attacks on Fiat Shamir that affect GKR. And we have some custom gates to have better performance on that. For the range checks, we start with a technique that is basically a lookup argument. The idea is you want to prove that something is within 0 and some bound B. What you do is you check if that value is inside the lookup table. That's a lookup argument. The problem is the lookup table would be very big because FHE ciphertexts are very big. And this is the example of a size for the thing that we would need to check. This is the size of the lookup table. It's obviously huge. And for integers, there is a solution for that. Lasso is a very good solution for that. And what they do is basically represent this huge lookup table as several small lookup tables that are recursively composed. So they get something very efficient for checking integers. But we don't want integers. We want to check things directly over the ring. So that's what we introduce here. We basically extend Lasso to also decompose the ring and be able to provide these range proofs directly over the ring. The last piece of our proof is the polynomial commitment scheme. It's that last component that I showed. Very high level, everything that I showed so far, the other building blocks, they will generate some checks and polynomial commitment operations, which is where the cost is. And since we have a special ring, we need to find a polynomial commitment that was compatible with it. A very easy solution was the breakdown polynomial commitment because it's field agnostic. So it works for anything, so it works for our ring. However, we don't have any ring. We have a special ring that is almost entity-friendly. So we take advantage of that and we optimize the breakdown for our specific ring, getting also about 10 times improvement in performance. Okay, that was basically our proof-friendly CKKS and how we prove it. We have some estimates in terms of performance, details in the paper, but just to give a very general idea, we benchmark each of the components, and our goal is really showing that each of the components that we introduce here are practical. If you combine these components naively, you would have a few seconds per multiplication to prove a CKKS multiplication. It scales linearly for the prover, sublinearly for the verifier. We have a very efficient verifier. And of course, we are also working on ways of composing these components that are non-trivial and that gives better performance for large circuits. And we should have better performance for large circuits as well. Thank you.
We have time for questions. So I have a question. I think you mentioned it a little bit, but the fact that you're using GKR, is the attacks on GKR in the Fiat-Shamir thing apply anywhere to your scheme?
So it doesn't apply to us because we have this very structured GKR. So it always has depth 4. And we put the size of the FHE circuit, it increases the width of GKR and not the depth. And we have a lot of commitments to GKR as well, so it really doesn't affect us.
Thank you.
Thank you, great talk. I want to elaborate a little bit more on the efficiency side. I know you shared some numbers, several seconds for multiplication. In terms of relative cost, relative overhead, let's say there is the CKKS computation itself, and now you add verification to it. If you could give an idea of the order of magnitude that you're looking at.
Yes. Essentially, our implementation of CKKS, we are doing a Python implementation with a backend in C. These are the parameters for these values. So the basic multiplication of CKKS without the proof-friendly ring would take 7 milliseconds. Once you put the proof-friendly ring, you go to this. And for this parameter, I don't remember the time, but if L was equal to 3, which is the one that I mentioned, we would have, if I'm not mistaken, 20 seconds to prove one multiplication.
Like 3 orders of magnitude, basically.
Sorry?
3 orders of magnitude, essentially, roughly. I mean,
Yes.
is it kind of applies to various operations, or it's just like the 3 orders of magnitude, or it's just specific to this operation?
No, it's specific to the multiplication at the first level. As you go and you drop some RNS components, things will get faster. Even though we're still working over the same ring, we consider those zeros and we make things faster as you drop RNS components. And also one thing that I think I should stress is that this is just taking these building blocks and composing them kind of naively. So we are working on better ways of doing it so that you have a better circuit, a bigger circuit, you can do that much faster. We're currently working on that.
Okay, thank you.
Thank you.